Hiral is also there. Morning, Hiral. I hope you're well.
Morning.
So let's get started. So today I'll be talking about types of solutions and properties, types and properties of solutions. And we'll mainly be focusing on the pharmaceutical practice and what this means to us. So essentially, solutions can either be classified as I'm here, types of solutions. So they can be classified as either gas, liquid, or solute, depending on whether the solute is a gas, liquid, or solid, or if the solvent is a gas, liquid, or solid. So we can have solid, solid, liquid, liquid, gas, 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 liquid, all those different combinations present. But in the pharmaceutical practice, we'll mainly be focusing on the solids being our solutes and the solvents being liquids to form our solutions. So first thing we look at is vapor pressures and how they affect the solutions. And I'll start by stating this kinetic theory of matter, which indicates that thermal motions of molecules of a substance in a gaseous state are more adequate to overcome the attractive forces that exist between molecules. Let me repeat that. The kinetic theory of matter indicates that the thermal motions of molecules of a substance in gaseous state are more adequate to overcome the attractive forces that exist between the molecules. What does this mean? This basically means that the thermal motions which are usually present in the gaseous state are the reason why gases have so much intermolecular spaces between them, meaning that the thermal motions which are present in solids, they're not adequate enough to overcome the attractive forces present within the solid. And that's why solids are usually together, then liquids are less together, and then gases are more split away, like they have larger spaces between them. And then, as like now, unlike the gases, liquids occupy a definite volume with the surface. And whilst there is evidence of structure within the liquids, such structure is less apparent than solids. So just what I've said, these thermal motions are not stronger, are not as strong as those in the gaseous state. Yeah. So if temperature is maintained constant, equilibrium can be established eventually between the vapor phase and the condensed phase. So condensed phase is what we have when we have solids, and vapor phase is what we have when we have liquids. So if we have an equilibrium and at a maintained temperature, we can, there can actually be an equilibrium between the vapor phase and the condensed phase in that, equal amounts of gases and equal amounts of solids on both sides. And the equilibrium, the vapor at this equilibrium is what we call vapor pressure. So vapor pressure, basically, the pressure exerted by vapor at this equilibrium between the condensed phase and the vapor phase. So, however, the pressures exerted by solids are usually much lower than those exerted by liquids because the intermolecular forces in solids are stronger than those in liquids. Sorry, let me switch off my phone. So, and because the intermolecular forces between solid solutes and liquid solvents tend to be relatively strong, such solid molecules do not generally escape from the surface of a solution nor contribute to the vapor pressure. So I think all that is just self-explanatory. But if anyone has a question, please feel free. So second thing now we'll be looking at ideal solutions and non-ideal solutions just generally. And basically the concept of an ideal solution was introduced so that now it can act as the standard when we're comparing it to non-ideal solutions, because in itself, like ideal in all aspects of life is just, it's almost impossible. But this perfect concept is what we will use to compare to the non-ideal solution. So non-ideal solutions are also known as real solutions. So solvent-solvent, solid-solvent, and solid-solid interactions are the same and equal to strength of intermolecular interactions in either the pure solvent or the pure solute. Now this is essentially in our ideal situation. And since solutions are homogeneous just by definition, the relative number of these surface molecules will be the same as the relative number in the whole solution. Yeah, I think that's also self-explanatory in that, like just basically what we're trying to say is all our mole fractions of both the solute and the solvent will all equal to 1. So if we take an equation where x1 is our mole fractions of the solute, x2 our mole fraction of the solvent, x1 plus x2 should give you 1 in our ideal situation. And now if we change that to our vapor pressure, P1 for the solute, P2 for the solvent, it should equal P, which is the vapor pressure of the whole solution, or the binary solution, or the ideal solution. So in terms of the Raoult's law, it states that partial pressure exerted by a volatile component in a solution at a given temperature, let me repeat that, partial vapor pressure, P, exerted by a volatile component in a solution at a given temperature is equal to the vapor pressure of the pure component at the same temperature, multiplied by its mole fraction in the solution. So basically, in an ideal solution, if you take the vapor pressure of that solution, just of that component, whether it's the solute or the solvent, if you take the vapor pressure of it itself within the solution and you multiply it by the mole fraction, yani the amount of that component in it, it should give you the vapor pressure present in the whole solution. So one of the consequences of the preceding comments, like just what I said, means that like just basically ideal solutions obey the Raoult's law. However, like we don't expect like these ideal situations really, because as I said, you know, ideal is just a perfect world. But mixtures which exhibit an ideal solution, example, benzene and toluene, N-hexane and N-heptane, ethyl bromide and ethyl iodide, and binary mixtures of fluorinated hydrocarbons. So those systems now, those specific ones will exhibit an ideal behavior. So now let's look at the non-ideal. So basically the idea is in ideal solutions between the solute and the solvent, or solvent-solvent, or solute, the forces of interaction between them are usually equal. But now in non-ideal, they are unequal, the forces of interaction. So just picture it as if in an ideal solution, it's sort of like the forces of attraction are kind of at an equilibrium, in that one side you have them separated and one side you have them diluted. So in an equilibrium. So they're equal amounts when they're separated, as they are in equal amounts when they are diluted. But because our forces of interaction are unequal in non-ideal situations, then now we have to use the mole fraction to really understand, what amounts were, because things are just unequal everywhere. So for these equations of non-ideal, we substitute for each concentration X, as a measure of like just the effective concentration. X is our mole fraction. And now we can use, and we can tell which amount is which by using the thermodynamic activity. So basically, this equation where we are using the thermodynamic activity as A, if you multiply it by the vapor pressure of the solute or the solvent within times the thermodynamic activity, which is also the effective concentration or the mole fraction at that particular time, which will give you the vapor pressure present. And this equation in itself can be used in both ideal and non-ideal situations. So I mainly just focused on the things that we need to look at, because there's no need of us just going through the whole textbook. And so although most systems are non-ideal and deviate either positively or negatively from the Raoult's law, such deviations are small when a solution is dilute. This means that, like already, like the forces of attraction are enough to form a dilution. So the deviations from the Raoult's law are just pretty small. So next thing now, I'll look at ionization of solutes. Remember, solutes are put inside the solvents. So many solutes dissociate into ions if the dielectric constant of the solvent is high enough to cause sufficient separation of the attractive forces between the oppositely charged ions. Such solutes are termed as electrolytes, and the ionization or dissociation has several consequences that are often important in pharmaceutical practices. Yeah, I think that's just self-explanatory. So we will start by looking at water, and this in itself is the reaction that water goes through each and every second. I think it's important to also appreciate that we can have a further reaction where now if we, as my arrow, I'm sorry, I'm not really an artist, but we can also yield, more complex ions. And here I put a plus there. So, but in this case in itself, we'll just mainly be looking at this reaction. So let me just erase that. So So in pure water, the concentrations of, the hydrogen ions and the OH or the hydroxide ions are equal. And at 25 degrees Celsius, both have the value of 1 times 10 to the power -7 moles, per liter. The Lowry-Brownsted theory of acids and bases defines an acid. Lowry-Brownsted, you can remember that from first year, second year. I think we've also done it recently. Defines an acid as a substance which donates a proton. So in this case, our acid is obviously H plus, donates a proton, a hydrogen ion, yeah. Yeah. And obviously our hydroxide ion in this case is the one receiving the proton. So basically, please note that the arrows are pointing both sides. So at equilibrium, if our hydrogen ion donates a proton, basically now we'll just form our H2O on the other side. So now we'll introduce the concept of pH as a more convenient measure of hydrogen ions. And pH is defined as the negative algorithm of the hydrogen ion concentration. The negative logarithm, of the hydrogen ion concentration. So pH is equals to negative log over hydrogen ion concentration. Important to appreciate, in a neutral solution, our pH is 7, both of the hydrogen ions and the OH, because now they're just together. Yeah, and the pH in itself has important implications in pharmaceutical practice. Some of them are the degree of ionization of drugs that are weak acids or weak bases, solubility of drugs that are weak acids or weak bases, ease of absorption from the blood, based on whether they're weak bases or they're salts. And for weak bases or salts of weak bases, the drugs dissolve more rapidly in low pH of the acidic stomach, and this is just, plain and simple, because they're being, like, we're forming a neutral solution, which can then be easily taken up, because the pH in the stomach is acidic, so it's reacting with the bases, and then now we just form a neutral solution, which is easily taken up. And important to note that many drugs, about 75%, are usually weak bases or salts of weak bases. So also used for stability of many drugs, to determine the stability of many drugs, and also just to tell how they'll react in different body tissues, where both extremes of pH are injurious, because if you have excessively dilute, excessively acidic, or excessively basic, it can be bad. So now we'll introduce the dissociation constants. And basically, this is just the reaction of an acid, and this is the reaction of a base. So our acid can be split, a weak acid, HA, can dissociate to have both, because it's weak, it has both hydrogen ions and the base ions as A. And for a weak basic drug, if you add hydrogen ions, then now you'll form, the BH plus. So in solutions of most salts of strong acids or strong bases in water, such equilibria are shifted strongly to one side of the equation because the compounds are virtually completely ionized. Remember, strong acids, strong bases, we expect complete ionization. While for weak acids and bases, we almost have an equilibrium between whether it's the weak acid or the hydrogen ions and the basic ions are sort of dissociated. So our ionization constant is usually Ka of our partially ionized weakly acid species and can be obtained by the application of the law of mass action to the yield. So from this equation, I plus and I minus are the concentrations of the dissociated ionized species, and U is the concentration of the unionized species. So if you multiply the ionized species for each other and divide by the unionized, then we'll find the Ka. So for weak acids in themselves, we know that our ionized species are both the hydrogen ions and the basic ions, which will say A minus. So if we do H plus times A minus divide by HA, we expect to find the Ka, or the dissociation constant of the acid. Yeah. Now we can remember when you're turning everything to logs, everything which was a multiplication is now an addition, and everything which was a division is just a minus. So look at this. So now logarithms. So log Ka is equals to log to the base of 10 of H plus the log of the basic ions A minus the log of our unionized species, which is HA. Yeah. So if we reverse everything from this equation and everything which was a plus, now we put it as a minus, we will remain with only this as a plus and everything else as a minus. And basically, the symbol of pKa is used to represent the negative logarithm of the acid dissociation constant in an analogous way that pH is used to represent the negative logarithm of hydrogen ion concentration. So therefore, pKa is equals to negative log of Ka. So remember, pH is equals to the negative log of H. So pKa is just basically the negative log of the dissociation constant. So P logarithm. So, and we can now write it down as pKa is equals to pH plus log HA minus log A minus. What does this mean? Just look at this equation here. And we've said logarithm is P. So pKa is equals to pH plus the logarithm of the A minus the hivyo tu venye imeandikwa, like now substitute the logarithm which was meant to be here for P and the logarithm of the hydrogen ions for P. It's just the same thing. So pKa is equals to pH plus, as we said, like log, you can like minus in log is equal to just division. So log 10 evo. And then now when we shift the whole thing and take it to the other side, so we take this and take it to the other side. You bring it here. Instead of turning this into minus, all we have to do is just find the reciprocal of this. I don't know, if you're good in logs, like it's pretty easy to understand. Personally, I didn't really have an issue, but if anyone has a problem, I could take it a bit slower. Yeah, don't feel shy, just barge in anywhere and, tell me where the problem is. So basically just the same thing for the acids, like just the same process. Yeah.
Willy,
Niambie.
Burudi juu kidogo nipige screenshot.
Pole. Hapo.
Yeah. Okay, thanks, man.
Are you understanding, Ahmad? Would you want me to do it again?
Logs are not for me. I'll just have to go through them slowly. Don't worry.
But it's not a long topic, so you can just grab your pen and your paper. I'm saying it's not a long topic, so you can just grab your pen and your paper, and we can go through it a bit slowly. Where we write down pole. We have that. I think in the next 20-30 minutes I'll be done with it. So just grab your paper, and then we can look at it slowly. So I'll start again from this reaction here, the one we have here. So Ka, even me I have my pen, is equals to H, A minus over HA higher. So we've said if we turn everything to logs, multiplication is usually addition and division is usually minus. So log Ka is equals to log H, here H plus log here A minus minus, because now the HA is division, log HA higher. Basically, this first equation here came about because we said to find the dissociation constant, you find you multiply the ionized species, divide by the unionized. So HA is not ionized, H plus and A minus are ionized. So we've just written down this equation, and then everything which was plus, we turn it to minus, and then we get this equation here. Higher. We said log negative algorithm. We can dissociate, like P is our negative algorithm. If it's Ka, it's our negative algorithm of the dissociation constant. If it's pH, it's the negative algorithm of the hydrogen ions. Sindio?
Your negative, how is it coming out? Like what's the essence of it?
So basically, P in itself is the negative algorithm. Sindio? Like generally, when we say pH, it's the negative algorithm of the hydrogen ions. So tumefanya kila kitu kwe negative hapa, ndo tuweze substitute easy negative logarithm, tuweze substitute easy negative algorithm na P. You understand? So hakunanga. So hapa in this equation here, our negative algorithm of pKa can be over KA can be PKA sasa. To substitute, instead of kutumia negative log 10, tutatumia P. Haya. Is equals to PH, sindio?
Yeah.
Minus E log 10 ya A minus plus log 10 ya
Iko hiyo the other side.
No, niko hapa. I'm just E KA nimeitoa, E negative log ya KA substitute na P. E negative ya H plus nimeweka P pia hapo. Si ndio?
Okay. So hiyo ingine itakuwa P into
hizi hakunanga PA. So tutatumia tu negative log 10 A minus now plus log 10 H plus. Hizo hatutasa. Ndio?
ya H tuna substitute ama side ya log
PH, si tuko na PH, tunajua PH ni kitu. So tuta substitute hapo pia. Ndio?
So yenye itabaki ni minus log 10A
minus na H plus, ndio?
HA plus, ndio?
Okay. Haya. So venye tu tumesema P ni negative algorithm. So PKA is equals to negative log 10 of KA. Sindio?
Yeah.
Higher. So the equation in itself can be rewritten as PKA is equals to PH. Sasa note everything, because PKA haina, hatutaweka hiyo plus or minus. Sahi tukitumia hii P in itself, everything which was plus will be minus and everything which was minus will be plus. Let me repeat that. Because when we're using now P in itself, we eliminate the idea of negative log within our equation. Everything which was plus will be minus, other than the things which already tumezipea P. So from the equation which we just written down here, when we substituted P, now from here down, negative log A was minus. So tukikuja hapa, negative log, no, yeah, it's still the same, sorry.
The same.
Sorry, the same. Yeah, so this equation is just basically everything which was negative log, this first two tumezipea P, na hizi zingine tu zikabaki tu venye ziko. So as we said, logarithm ukidivide, ukiminus divide, ndio? So PKE is equals to PH, and since it's log 10 HA plus, minus log 10 A minus, tunaweza andika hiyo as log 10 HA on top divide by your A minus, sindio?
Yeah.
Higher. And that's just basically how we get the equation in iko hapa. And then if we take the equation on the other side and everything else on the other side, now we can just do a reciprocal. So itakuwa EPKA, this side, itakuwa plus log 10 alafu reciprocal ya EA minus over HA, which we get here. And this is the Henderson-Hasselbalch equation for weak acids. Obviously, itanidi uiangalie tena, but this is just the basic idea. Yeah, just note, instead of ukiipeleka on this other side, instead of kuweka minus kwa hii log, unapata tu reciprocal. And just the same thing will happen when we're using now a base.
Okay.
So, are we a bit better?
Yeah. Now I'm okay.
So now how do we use, oh no, let me, yeah. Yeah, I'll just, easy is in a, it's just a diagrammatic representation of just basically what you see. Didn't really find too much importance in it. So let me just go to the use of the Henderson-Hasselbalch equations to calculate the degree of ionization of weak acids or weak bases. Best thing is, I think there's some questions here, so we'll look at them in a few. So the degree of ionization of a drug in a solution can be calculated from the rearranged Henderson-Hasselbalch equation for weak acids and weak bases. If the pKa of a drug and the pH solutions are known. The resulting equations for weak acids and weak bases are as written down respectively. So for weak acids, tuko na hii hivyo tu venye tuliandika from here. If you take everything else on the other side, like just iso substitution too. Yeah, the best way to explain it is using this. So basically, if we take our pKa to the other side, equate pH minus pKa is equals to your log A minus over HA. Or just the other way around, if we take our log to the other side and our pKa to the other side, it will be pH minus pKa is equals to log, yeah, hivyo tu venye log imeandikwa. Haya. And for our bases, basically just the same thing. So basically what we're trying to say is pKa minus pH will give us the log of our unionized species over the ionized species. So these are examples of equations that we can use. So the pKa of aspirin, which is a weak acid, is 3.5. If the pH of gastric contents is 2, don't even know what the hell this question is asking, but basically it's just asking for, what we get from pKa minus pH. So if anyone has a calculator, just take it out. So pKa of the weak acid, tumesema ni 3.5, sindio? Minus the pH of gastric contents is 2. We get 1.5. Remember, 1.5 is our log of our HA divided by A. So find the antilog of that. I haven't used a calculator in so long. And you will get this 31.6. So the ratio in itself is 31.6 to 1 of this. Is anyone not understanding? We can also do the second one. pH of plasma 7.4. And we'll use the same pKa of this aspirin that we've looked at here, 3.5. So pKa minus pH. So 3.5 minus 7. 7.4, sorry, plasma. And then you just find the antilog of that. Antilog. Yeah, and this is what you get. And this is the ratio of the unionized to the ion. So I think Yeah, I think that's kila kitu iko sawa. So this is just, like I've never been a very big fan of just cramming equations, because then you never know how exactly to input what. So but from this reaction, how we got, just to explain how we get this, remember, pKa minus pH. So we'll take pH to the other side, we'll take log to the other side. Instead of doing the log minus log A minus over HA, we can just find the reciprocal. So log HA over A is equals to pKa minus pH. So just remember, instead of putting minus, you can always just find the reciprocal of our log. Cool. Important to note, like just in buffers, the ability of a buffer to withstand the effect of acids and bases is an important property, and this is what we call the buffer capacity. Buffer capacity, ability of a buffer to withstand the effects of acids and bases. Yeah, because it's important to know, obviously, if we add large amounts of acids or bases, our ratio of an ionized to ionized will completely change. So we determine buffer capacity by its ability to repel or withstand those effects. So next thing we look at is colligative properties. So tumemalizana na hizo ma Henderson-Hasselbalch, but just please note that log of the unionized over ionized is equals to pKa minus pH. That's all you need to take away from what we looked at. So when a non-volatile solute is dissolved in a solvent, certain properties of the resulting solution are largely independent of the nature of the solute and are determined by the concentration of the solute particles. Let me repeat that. When a non-volatile solute is dissolved in a solvent, non-volatile, certain properties of the resulting solutions are largely dependent on the solute and are determined by the concentration of the solute particles. So when we talk about colligative properties, we are mainly talking about a non-volatile solute. And basically, we're just saying that this non-volatile solute will determine the properties of the resulting solution. So non-volatile, we just mean it won't escape. Sindio? So whenever we have these solutes which do not escape, they're the ones which mainly determine the properties of the solution which we have, because they're always just present. Higher. In the case of non-electrolytes, the solute particles will be the molecules, but if the solute is an electrolyte, then its degree of dissociation will determine whether the particles will be ion only or a mixture of ions and dissociated molecules. This means that if we have like acids and bases, they can either form ion only or a mixture of ions and undissociated. Likewise, if it's non-electrolyte, then like we'll just have molecules which are not charged. And the most important colligative property which we'll look at is osmotic pressure. However, there are other important ones such as lowering of vapor pressure of the solvent, elevation of its boiling point, and depression of its freezing point. So boiling point, freezing point, and vapor pressure. So basically, what are we saying? We're saying that osmotic pressure is mainly determined by the solutes. Likewise, even in the solution, The vapor pressure, boiling point, and freezing point will also be determined by the solid within a solution, provided it's non-volatile. So, easy way to just remember, if you if you if you're making tea or whatever, like you can't see it boiling and then you start adding sugar there. You know that it will just start going up immediately. Meaning that the solid, which is sugar, which is non-volatile, will directly impact the boiling point of that tea. And that's why the tea rises. I hope that, I don't know. Honestly, me personally, I've never even made tea in my life, but like I know. So I'm pretty sure you guys also know. So osmotic pressure. But I hope you guys have experienced that. If you do have like hot tea, even in a cup, and you go and add sugar, like sometimes it just starts tripping. Anyway, osmotic pressure. Basically, osmotic pressure of a solution is the external pressure that must be applied to the solution in order to prevent it being diluted by the entry of a solvent. So basically, it's just the osmotic pressure is just an external pressure, which is avoiding the dilution, of our solution. Remember, for dilution to occur, we're talking about a solvent coming in. So if we had like tea, the osmotic pressure would be, like how it would prevent if you're going to pour water, like how it would just prevent water from coming in and, just diluting the whole thing. But important to know that we usually have a semi-permeable membrane present between the two solutions. So external pressure that prevents dilution of our solution. That's all it is. This was just honestly my reaction mob too. But one thing you need to note is that free energy or chemical potential usually play a huge role in determining, like for example, temperature will determine whether osmosis will take place. Our chemical potential of the solution will also determine whether osmosis will take place or how rapid osmosis will take place. Ayabasi. So next we'll look at osmolality and osmolarity and just the difference between the two. So the concentration of a solution may therefore be expressed in terms of osmolarity or its osmolality. And osmolarity is the number of osmoles per liter of solution, and osmolality is the number of osmoles per kilogram of a solvent. Basically, like easy osmoles, they're just the amount of osmotically active particles in a solution. So for osmolarity, it's the number of osmoles per liter of the solution. Na hii hapa, osmolality, the one which you're not used to, is per kilogram. So one is per liter, one is per kilogram. Remember, the one which we're used to, osmolarity, that one is per liter, and osmolality, that one is per kilogram of the solvents. So isosmotic solutions, if two solutions are separated by a perfect semi-permeable membrane, i.e. a membrane which is permeable only to solvent molecules and no net movement of solvent occurs across the membrane, then the solutions are said to be isosmotic and have equal osmotic pressures. So we say something is isosmotic if they have equal osmotic pressures, and there is no net movement, meaning we have a perfect equilibrium between the two, which are separated by a semi-permeable membrane, which only allows solvent molecules to pass through. Isoosmotic, iso, similar, higher, isotonic solutions. If two isosmotic solutions remain in osmotic equilibrium when separated by a biological membrane, then now we say they're isotonic. So just the difference, isosmotic, a perfect semi-permeable membrane, while isotonic is a biological membrane. So remember, when we're talking about isotonic, we're talking about the body. Isosmotic, probably something in the lab, just, something which we've created. Higher. Hypertonic, obviously, we know it means a huge number of osmoles, and hypotonic is the one with a smaller number of osmoles. Yeah, and yeah, with that, I am done. Yeah, so that's just basically what we needed to look at. Yeah, honestly, not very complex stuff. I tried to highlight like the important notes I wanted us to look at, and that's it. I hope someone has a question somewhere before we call it a day. I really hope like someone has understood something and we just haven't, just passed time, because it's almost been an hour. Hey, like just thinking that you wasted a whole hour of your day, that's crazy. Guys, do you have any questions for me? Hiral, how about you?
No questions.
Did you understand? Was I being too complex, or was just reading the notes? I hope not.
No, I understood.
So guys, you can stop recording, please. Is it even still being recorded? Yeah, it is. Let me text him directly and ask him. So I hope to meet you guys in the afternoon, in the evening or afternoon, because now we'll be having classes. I think we'll be meeting earlier. I don't know. Yeah, but I'm extremely grateful. I hope you guys have a great evening. Thanks. Thank you. Okay.
Thank you.
So God bless you guys. Bye.
Guys, what time are we meeting? What Hiral or Diana? Anyone?
Whatever is comfortable with you, I think. Because I don't know if we're doing the past papers with the other university students. I'm not sure about that.
I think guys and Diana are in a better position to tell us.